Hello folks, in Math 176, this is the first of 4 videos that will sort of give a couple of explanations of some of the in-class examples that we would have gone over had I not been unwell last week. So the first video is about 10.1, so before you get into it too much, be sure to look in Blackboard because I've posted these problems and their solutions, which is what I usually hand out to you in class, but I've also posted a summary where I've just gathered all the definitions and propositions and theorems and whatnot from 10.1 through 10.4, which might be a handy reference since, again, we didn't have class to go over it. So before you get started on watching these videos, at least go through, look at the slides and the formula handout for 10.1, and then watch this video, and then once you've done the same thing for 10.2, you can look at the next video and so on, okay? So basically I'm saying you're not going to learn chapter 10 from these videos strictly. They're going to be short and just cover a couple of the ones that we would have done together in class. Okay. So for 10.1, this is where we start introducing ourselves to some of the more graph-related topics, chapter 10. And so you should have read through the definition of graph, edges, endpoints, connected graphs, things like that. So for number 3 in 10.1, our goal is simply to create a graph from this information. And so I can see that my graph is supposed to have exactly 4 edges, and it looks like based on this that my graph should have 3 vertices. So I'm just going to draw 3 vertices and label them as follows. And then I'm going to make edge 1 go from vertex 1 to vertex 2. And I'll label that edge 1. Edge 2 should also go from vertex 1 to vertex 2. And edge 3 should go from 2 to 3. And edge 4 starts and ends at vertex 2. So that's one of those loops. And that's all of it. Okay, so that's number 3. That's all we need to do. We figure out how many vertices we have and then how many edges we have, and we connect them based on this graph. All right, for number 5, our job is to take this completed graph and relabel everything to show that it's actually the same as this graph. So all we need to do is label these vertices in such a way that, that it could be shown to be the same, an equivalent graph to this one. And the way we would show it's an equivalent graph is we could make one of these charts for this one and the same chart for this one and show that it ends up being literally the same chart, okay? So we don't need to work too hard to do this. If you kind of imagine this graph right here, if I were to pull vertex 5 down, what would happen is that imagine this as like the top of an umbrella, or like patio, also an umbrella, I guess. But if you pull this, this would hinge down, and eventually if you pulled it far enough, this peak would become a peak down here with a long handle hanging out of it. And if you thought about that, what that would look like, it would kind of look like that upside down, right? So one of the things we can do is realize that if this is supposed to be equivalent to this, then if we find a vertex with one edge coming out of it, and there's only one of them here that has one edge coming out of it, that's got to map up with the one vertex over here that has one edge coming out of it. So I know that this is vertex 5. And once I know that the only connection it has is to vertex 2, and that's using edge 6. So we've got part of it labeled. And then from there, vertex 2 goes to vertex 6 and vertex 4. So We'll make that vertex 6, that vertex 4. And those edges from 2 to 6 is edge 7. And from 2 to 4 is edge 5. And then from 6, the only other thing that 6 is connected to is vertex 1, so that one goes there. And the only other edge that vertex 4 is connected to is vertex 3. And that means we've labeled all of our vertices, so then we just finish up with the edges. Between 6 and 1, we have edge 1. And between 3 and 4, we have edge 4. And then from 1 to 3, there's edge 2 and edge, I might have forgotten to label it on here, so let's call that edge 2, and who's missing? 1, 2, I'm going to say it's edge 3. So that guy's probably missing an edge 3. Okay, and then a third example here is to answer a few specific questions about this graph. So from this graph, our first question for question I is, find all edges that are incident on vertex 1. Well, remember what incident means. Incident means that vertex 1 is one of the endpoints for those edges. So if we look at vertex 1, we can see that edge 1, 2, and 3 come out of that. So that's our answer there. For part 2, find all vertices that are adjacent to vertex 3. So here is vertex 3 right there. And the list of vertices that are adjacent to that are the ones that it's connected to by one edge. So it looks like from vertex 3 we can get to vertex 2. And we can start at vertex 3 and land at vertex 3. And we can also get to vertex 1. So it looks like vertex 1, 2, and vertex 3 itself are the list of vertices that are adjacent to vertex 3. So pay attention to that, that vocabulary. Incident, when you're talking about what's incident to a vertex, you're talking about edges. And when you're talking about what's adjacent to a vertex, you're talking about other vertices, okay? But similar kind of concept. And then for Roman numeral 3, find all edges that are adjacent to edge 1. So edges that are adjacent to edge 1, which edge 1 is here, right there. So the ones that are adjacent to that are ones that share a common vertex. So edge 1 is connected to vertex 1 and vertex 5. So the other edges that are connected to vertex 1 are edge 2 and edge 3. And down at this end, the other edges that are connected to vertex 5 are 8 and 9. So that's our list there. And for Roman numeral 4, find all loops. Well, loops are the ones that start and finish at the same vertex. So edge 6 and edge 7 are those. And then for question 5, Roman numeral 5, find all parallel edges. Well, parallel edges are the ones that have the same endpoints. So edge 8 and edge 9 connect the same two vertices. So edge 8 and edge 9 is one pair, and then edge 4 and edge 5 are another pair. They are not parallel to each other, these pairs, but they're within the pairs, they're parallel. And the next one is find all isolated vertices. Well, isolated vertices are the ones that are all by themselves, and I think once again I forgot to include that in when I was copying this down. So if you look at the example that we're looking at, vertex 6 is hanging out there. It's isolated because it has no edges coming in or out of it. So that is our answer there. And for find the degree of vertex 3, okay? So vertex 3's degree has to do with how many how many edges start or end at vertex 3. So we've got 1, 2, 3, 4, and 5. So this loop, edge 7, counts as degree 2 because it comes out of vertex 3 and it comes into vertex 3. So the degree of vertex 3 is 5. 1, 2, 3, 4, 5. Okay. So if we were to zoom in on it right there, you'd see 1, 2, 3, 4, 5 things coming out of it. And find the total degree of the graph is our last question. And that's just adding up the degrees of each of these vertices. So if we start with vertex 1 has a degree of 3. If you look at that, then we move on to vertex 2. Again, if you look around it, 1, 2, 3, 4, 5. And then vertex 3, we've already established, has a degree of 5. Vertex 4, 1, 2, 3, 4. And vertex 5, 1, 2, 3. And if we add those all up, we get 20. Okay, and that's your video for 10.2. Once you have reviewed the material for 10.1, once you've reviewed the material for 10.2, watch the next video. Thanks.